Last week, we've seen how a neural network operates, how one layer propagates to the next, and how it's all really just like a big voting system. The aim of this week is to understand the learning part of neural networks, or at least part of it, the essence behind making neural networks improve. There will be some vague multivariable calculus kicking around, and I can't be sure what I said is 100% correct. Still, I'll try my best to cover everything through. Now let's continue from our example from last week. Let's think about a problem that the system could run into. A student outsmarted the admissions process and tricked the admissions officers into letting him pass the admissions process because he was able to get some internal information that, say, the SAT score was regarded incredibly highly in this admissions process. So he got a high score in the SAT and got into the university. But he is a poor performing student overall and quickly fell behind his classes, close to getting expelled. The head of admissions is really mad that they let someone like this inside the university, and so he calls out to the admissions team to change their admission strategy, such that in the future, they can make sure to reject students like this one and not make the same mistake again. Let's assume the output of this network is just a simple 0 or 1. Where values first are in the range of 0 to 1, but below 0.5 is rejection, and above is acceptance. So they just turn to 0, 1 in the end. For the tricky student, their current score is 0.87, which corresponds to acceptance. And let's think, what factors can be changed such that this number can be lowered to below 0.5, so that a student like him will be rejected in the future? Oh yeah, forgot to mention this last week. The first and last layer of a neural network we call the input and output layers respectively, and we won't have activation functions nor biases on both of these layers. But we do in this case for the output layer for the sake of classification to switch things between 0 and 1. Let's look to the connection between the last layer and the previous layer. As we know how linear layer works, the value of this output neuron is dependent on the value of the previous layer's neurons and their weights connected to this layer. If we lower the weights connecting to this output neuron from the previous layer, the output neuron's value would go down. Okay, again, I'm simplifying things. If there was a neuron in the previous layer that had a negative value, tuning its associated weight larger would also lower the output neuron's value. But we're not going to discuss about those in this case. Positive values are easy to understand. If this neuron had a bias, we could also think about lowering that value as well. Or even further, we could try lowering the values of the previous layer's neurons. But how do we do that? Well, you sort of see a recurring relationship here. You'd change the values of the bias of the previous layer's neurons, the weights connecting to them, and the values of the previous layer's neurons. As again, neurons are functions determined by its bias, the weights connected to it, and the neuron values of the previous layer. We can't do that in this case, as that's the input layer, but you get the idea that we can go backward further and further in the network to change these parameters. You can think our network/voting system as having so many of these knobs and dials that we can play around with to influence that final output, given a specific set of inputs. In the end, we want to tune it such that the output goes from something undesirable to desirable. You can think it like playing with synthesizers and all the different knobs that you can twist to get some sound that we like without knowing what each knob does. Sorry, I'm just having too much fun with this, though I have no clue what I'm doing. So this raises a lot of questions. 1. How far do we tune these values up and down? 2. How do we know which values to tune? And 3. How can we do this systematically? The whole idea of learning and machine learning is just answering the question of how to do this number tuning. The formal name is called backpropagation. To do this, we introduce the idea of a loss function. Some call it a cost function, but same thing really. A loss function is a way to measure the performance of the network, how far its current outputs are from the desired outputs. The function itself could be really simple. For instance, we can take our tricky student example, and right now the network outputs 0.87, but we want the output to be 0. We can take the loss as the difference between the current output and the desired output. Using a simple subtraction, the loss would be 0.87 minus 0 equals 0.87. Now, with a loss function, we have a mathematical way to describe how much the network's outputs differ from the desired outputs. With the tricky student example, we have a loss of 0.87, and that's pretty large. But if there was another student whose predicted output was 0.04 and the desired output is 0, the loss is small. It would be 0.04. This tells us the network is making a much smaller mistake in the second case. This gives us a clear goal: to minimize the loss function's output. In other words, we want to tweak the network's parameters to reduce the error as much as possible. However, loss functions are rarely this simple in practice. A network can produce multiple outputs, a list of values called a vector, and we would also have a corresponding list of desired values. If we simply subtracted the outputs from the desired values and summed up all the differences, we might end up with something close to 0 just because the addition between positive and negative differences could cancel each other out. Or we maybe even end up with negative values, which wouldn't help us accurately reflect the network's performance, as there is no good meaning to interpret a negative value here. One common approach is to square the differences between each output and the corresponding desired value, and adding them all up, as now all differences must be positive due to the squaring. We call it the mean squared error, but of course that isn't the only way to describe the loss. The true loss function that should be properly used here is the binary cross-entropy loss. But we're definitely not getting to that, as I personally don't well understand information theory and cross-entropy loss. Before stepping on to the maths of how to do the rest of the steps in backpropagation for a neural network, I'll talk about the mathematical idea of something similar for a simple line trying to fit plotted data: linear regression. For example, imagine you're trying to predict the price of a house based on its size. We can collect data on house sizes and their associated prices, then plot them out on the xy plane, where x is the house size and y is the house price. In linear regression, we would try to find a line that best describes the relationship between these two variables: the input, like house size, and the output, like house price. Basically, it involves finding a line that minimizes the overall vertical distance between the line and all the data points. The equation of this linear line can be written as this: y equals ax plus b, where a is the slope and b is the constant. The smallest overall distance is basically analogous to the loss, and can be described with the mean squared error. But again, how do we minimize this function? Now is when I have to introduce multivariable functions and multivariable calculus. Think of it this way: as we adjust the values of a, the slope, and b, the intercept, the output value of the cost function changes accordingly to the overall vertical distance from the line to all the data points. So the cost function is a function that takes in two variables, a and b, and outputs one value. And here's a plot visualizing the value of the loss as we change the values of a and b. It's called a contour plot, basically a 3D surface projection onto a 2D surface, with color representing height of the function. Don't worry too much about the naming of x and y. X is just the slope of the line a, and y is the constant of the line b. I say it wouldn't hurt to think about it like weights and biases. We know that in calculus, sometimes we can find the minimum of a function explicitly by setting dy over dx equals 0, and then solving for the specific value of x. For more complicated functions, we might get into some things called locominimums, locomaximums, and saddle points, something that we'll worry about a bit later. But here, the loss function c depends on two variables, a and b. To find the minimum, we need to compute how c changes with respect to each variable, which we do using partial derivatives. So instead, we write partial dc over partial dA and partial dc over partial dB. Basically, how does c change to a and how does c change to b, respectively? Now, we can combine these partial derivatives into a single entity called the gradient vector. The gradient vector, denoted as nabla c, contains all the partial derivatives of c with respect to its variables. For our case, the gradient vector is as shown. The gradient vector tells you the direction of steepest ascent for the function at that point, a valuable property that we'll come back to in a bit. If you work your way through doing all this multivariable calculus by setting all the partial derivatives to 0 respectively, you'll eventually end up with a solution for A and B that guarantees you the line with the smallest overall distance to all data points no matter what the data is. And we can visually see that on the plot at about this point, as the minimum point just happens to have a loss value of 0. At a minimum, the function does not increase or decrease in any direction. It's flat in all directions, and so all the partial derivatives are 0. Doesn't necessarily mean the function has a minimum of 0. As an 8XL student doing mathematics, there is a formula in your formula booklet for finding the value of A and B that would give you the lowest loss, given some set of data points for linear regression in S1, and I basically just told you how to derive that. Now, back to neural networks. Minimizing the loss function requires us to compute the gradient vector as well. However, unlike the simpler case of linear regression, we can't just set all the partial derivatives to 0 and solve for a minimum directly. Why? Because there are too many variables in the network and solving all those equations explicitly isn't feasible. There are also many instances of local minimums and maximums in our cost function where the gradient vector is 0, and there's no guarantee that we'll end up at a set of parameters that would give us a small cost function value. Instead, we calculate the partial derivatives of the cost function with respect to each variable in the network at our current value of the cost function, our current point. To make this concept easier to grasp, let's start with a simplified model. This part might get a little heavy on annotations and involve a bit of derivative calculation, but stick with me. Now what you see here is a neural network with two neurons, AL and AL-1. The input feature is X, the model output is AL, Y is the label, and C is the loss function. Now, as we know, a neuron is a function of weights, biases, and the previous layer's outputs. I'll expand our graph here a bit so every variable, every partial derivative can be clearly seen. These are the variables which we'll need to find their partial derivatives for. I'll now write out the definition of our loss function, C as mean squared error, the definition of the output of a neuron, Z before the activation function, and A, the value of Z after the activation function. Now, how should we find partial d C over partial d WL? Well, if we recall what I said earlier, the loss C doesn't directly depend on a weight WL, but depends on it indirectly through intermediate variables like ZL, the weighted sum before activation, and AL, the activation output. To compute partial d C over partial d WL, we have to see when we make a tiny change in WL, how does that affect ZL? And now that ZL is changed by a tiny bit, how does that affect AL? And now finally, in changing AL a bit, how does that affect our cost function C? This is what we call the chain rule in calculus. It's a fundamental concept in calculus that allows us to compute the derivative of a composite function. Of course, you could go brute force and just use the definitions I've given and expanded out our cost function to solve a single variable calculus problem. Though the chain rule is way more systematic and allows us to compute derivatives at each step of the network. So compute derivatives, shall we? You can do this yourself as a little exercise, but I'll just give out the answers here. Then we just simply multiply all of them together to get our answer for partial dc over partial dwl. We can compute out partial dc over partial dbl in a very similar fashion. Just swap out partial dzl over partial dwl with partial dzl over partial dbl and multiply them all together. So how do we go further back in the network? It's the exact same idea. Changing WL-1 changes ZL-1, which changes AL-1, which changes ZL, which changes AL, which changes C. It's just again multiplying all these partial derivatives together. And if you spotted it, you'll realize the last two terms have already been calculated when you were finding the partial derivatives for the parameters in the layer after it. This can go even further and further backwards in the network for like w L minus 2. And again, you'll find these four terms have already been calculated when we were finding the partial derivatives for the parameters in the layers after it. Though in my example, we don't have a w L minus 2 and onwards. Alright, I think we've covered enough for today. We've dived deep into how backpropagation works, starting with the chain rule, then systematically applying it layer by layer to compute gradients for weights and biases. This might feel like a lot to take in, and that's okay. It's the heart of how neural networks learn, and it's worth spending time getting comfortable with these ideas. The key takeaway is that backpropagation gives us a systematic way to compute how every parameter in the network influences the final output, so we can adjust them to minimize the error. Next time, we'll focus on how these gradients are actually used in gradient descent to update the network's parameters and make it smarter with each step. And here's something for you to ponder about. In my oversimplified example, I only had one neuron per layer, with one weight and one bias. How do these derivatives work when layers have multiple neurons and multiple biases? It's really not as hard as it sounds. Derivatives are distributive after all, so the math is mostly about finding how the summation sign works here. And another side note, when dealing with layers as matrices and vectors in backpropagation calculus, you may encounter derivatives expressed in vectorized notation in some resources. This often introduces operations like the Hadamard product or matrix transposes, which can initially seem confusing. Though really it's just the same thing written in a different format. What's shown here is an old note of mine trying to convert between the two notations.